So let me begin my talk. So see, astronomy is concerned with nature, and there are two important mathematicians, Euclid and Galileo. Galileo, of course, is concerned to be more kind of physicist than a mathematician, but he was primarily a mathematician, like Newton. Laws of nature are but the mathematical thought of God was said by Euclid, and Galileo said the laws of nature are written in the language of mathematics. So this claims by these two great people mean that mathematics has something to do really with the laws of nature, because astronomy is a science in its own right, and it behaves within the laws of nature. And therefore, once you talk about laws of nature, you need physics, you need mathematics, and everything put together. So mathematics, in fact, is a vital tool in understanding how celestial objects behave in cosmos and other things. And I will be highlighting some little part of those things. It not be possible for me to convey everything that is discovered so far in a short talk like this. Therefore, I will be primarily interested in conveying the significant part of mathematics involved with respect to astronomy. And moreover, I have chosen the topics in such a way that it is accessible to most of the participants, especially undergraduate students. So it will not be very tough mathematics. I think if you listen well, everyone can follow. But at the same time, you will be taken into very much surprise at the end of the talk to know how much of mathematics has influenced astronomy. Sorry. Please pardon me because I have cold and fever, so I have not recovered from the cold. So pardon me for coughing. So I would ask everyone this question when I talk about astronomy: why most of the celestial objects, not every object, but most of the celestial objects look round in shape? If you of course, in three dimensions, this is only the periphery of the object. So why does most of the objects look like spherical shape? Or if you just take the 2D image of it, why do they represent a circle like this? The periphery looks like a circle, including sun, celestial objects, whatever it is, most of the asteroids, most of the, of course, not stars or something like that. Even stars are round, but it look in different shape. That is a different thing. Okay, so most of the planets that we know, and most of the asteroids and small planets, whatever it is, cosmos objects look like round in periphery, including our famous sun, which itself is a bright star. Why do they look like in a round shape? So the answer lies actually in the fact of which can be explained by mathematics. That will be quite surprising actually, because it was answered by a theorem called isoperimetric theorem. So to explain this, what I have to do is I would ask you to take a piece of thread like that and ask you to make it in any shape, enclose it into any closed shape. And if you could do that, maybe you can fold it to form a square shape. That piece of thread can be folded into form a rectangle, can be folded to form a hexagon, can be folded to form a circle, can be folded to form, join the ends and fold so that you get an ellipse or something like whatever shape you want. Now, among all such shape that you get upon different foldings, if you find the area, because the same piece of thread is given to different students, in other words, the perimeter is same. That is why it's called isoperimetric theorem. The perimeter of the thread given to each student is same, but each student fold it in a different way to get different shape. Now, the students who had folded the thread into shape of circle will indeed have the maximum area. So with respect to 2-dimension, circle encloses the maximum area with a given perimeter. And this was answered by a very famous theorem called isoperimetric theorem. In fact, the isoperimetric theorem, which actually the proof involves calculus. So it says that the perimeter square of any enclosed region is greater than or equal to 4 pi times the area. So you get the maximum area when this inequality becomes equality. When the perimeter square exactly is equal to 4 pi r times area of the enclosed region that we have formed through the thread, then we get maximum possible area. And for a circle whose area is pi r square, if you substitute here, see for a circle, perimeter is 2 pi r, the radius of the circle is r. So squaring 2 pi r, you get 4 pi square r square in the left hand side. You can see it here. So this is 4 pi square r square in the left hand side. This is 4 pi into pi r square. Area of circle is pi r square. So 4 pi into pi r square. This is 4 pi square r square. So you get equality here if you choose a circle. And I told you that the theorem says for the shape that when you get this equality, that will be the shape which encloses maximum area, and therefore that happens for a circle, which means that within a given perimeter, same perimeter, circle encloses the maximum area. And within in 3D analog for this two-dimensional case, within a given surface area, sphere encloses the maximum volume. The inequality that we have here is that instead of perimeter square here, you get surface area the whole cube, because this is 3 dimension, that is 2 dimension. So the cube of the surface area is greater than or equal to 36 times pi times square of the volume. So this is a square cube relation, and this relation is very, very important not only for celestial objects. Most of the species also satisfy this this kind of curious relation actually. So this relation is very, very important even for mathematical biology. Okay, so and as before, the shapes which the objects which for which you get equality in this inequality will give the maximum volume for a given surface area, and that happens for a sphere. Because if you take a sphere of radius r, the volume is 4 pi r cubed by 3. Substitute that in the right hand side, then simplify. What you get an answer that will be equal to the answer here. This is 64 pi cube r power 6. If you simplify this, you get 64 pi cube r power 6. You get equality when you take a sphere of radius r. So this calculations and conclusions make us to understand the fact that among 2D shapes, circle encloses the maximum area, and among 3-dimensional objects, sphere encloses a maximum volume when surface area is a constant, when having same surface area. Therefore, due to this fact, probably we feel that the most of the celestial objects that we look at have spherical periphery or circular periphery. They have circular boundary, and the object themselves look like spheres because nature knows how best to optimize. Nature is the best optimizer. Nature knows how best to take and mold itself. Nature always chooses the best possible thing available. It is quite wonderful to see that most often, 9 out of 10 times, nature always chooses the best possible thing with it. So that's how we have to learn from nature, choosing best thing in our life. So what could be the shape of the earth? Most of the young children could immediately say that it's a sphere, but the exact mathematical shape of the earth is not an exact sphere. It is called ellipsoid, and I will explain to you. If the earth should be actually a pure spherical shape, then this is north pole and this is south pole. So if you measure the diameter of the earth through joining this topmost point and bottommost point, what you call polar diameter, this is north pole, the topmost point, this is south pole, the bottommost point. So if you calculate the diameter through joining the poles, north pole and south pole vertically, it would amount to roughly 12,714 kilometers. That's the diameter of the earth, polar wise, by joining the poles. Whereas this middle portion, horizontal line, is the equator. So if you compute the diameter of the earth through equatorial portion, that is through horizontal maximum portion, okay, the middle of this, you see that is 12,756 kilometers. So this is nearly 42 kilometers more when you measure through equator portion compared to the polar portion. So when you measure horizontally, the diameter is 42 kilometers more than the measuring with respect to vertically. How does this could happen? For a pure sphere, it doesn't matter in what way you measure. In fact, for a circle, all diameters are same length. It doesn't matter what diameter you take, it has same length, namely 2 times the radius. But here, if the earth could have been a spherical shape, all diameters that you take should have same length. But here you see the polar diameter is 42 kilometers less than the equatorial diameter. Therefore, this fact conveys a small thing that earth is not perfectly spherical. It is something similar to spherical shape, but not exactly. It doesn't differ much from spherical shape though, but it's not exactly spherical. I would probably compare the shape of the earth with the orange fruit, where if you take the orange fruit, if you see the topmost point and bottommost point are very flat. They are not quite round as here. See, here the orange fruit is quite round, but if you go near to the topmost point where we call the North Pole, it is quite flat there. Similarly to the bottom portion, it is quite flat. So such fruits, orange fruit is the best analog for Earth shape, and such where because the Earth is flat at the topmost points and bottommost point, North Pole and South Pole, the middle portion got little bulged. So if you press something here, the middle portion will bulge. So the middle portion, because of that bulging, will have a few kilometers in addition to the polar diameter, the vertical measurement. So that particular bulging shape of resembling a spear has a curious name, technical name called Oblate Spheroid. OVLATE, Oblate Spheroid. So the technical name for the shape of the Earth is Oblate Spheroid, which is actually mathematically is one of the family of surfaces called ellipsoid. So it's one of the ellipsoid. Ellipsoid, Oblate Spheroid is a special case of a surface name called ellipsoid. So this is an ellipsoid actually, but the technical name is Oblate Spheroid. Spheroid means an object resembling a spear obtained from a rotation of just like a spear, but it's oblate because it is bulging at the center. So it's oblate because the topmost and bottommost parts are a little flat over here, and therefore that's why you get difference in the diameter measurements here. Okay, so this is the reason. So this simple observations will make to think us more. So the name of the Earth is not sphere. If you are a well-trained scientist, you have to say that it's Oblate Spheroid. Okay, so that's the first thing that you have to learn about shape of the Earth. See, right from the ancient times, people started to investigate science by looking at the skies. Their first tool of investigation into understanding the science was probably the sky. So looking at the skies and marking the motions of the stars, positions, and other things, the celestial bodies, like how far the moon will take from full moon to new moon, and all those things. They calculated the number of days will take, and with the rough measurements that for a long span of time, like years together, like 30 years or 50 years of observation, they could probably come out to find that all things happen in quite cyclic fashion. Like a moon goes one complete round, and from new moon to another new moon, or one full moon to another full moon in roughly 27 days or something. So they calculated that Earth goes around the sun as a center in the elliptic orbit, in some orbit. Because they do not know elliptic quite surely. The ancient people believe that it went circularly. They believe that the object revolve in circular orbits. Okay, so but it does so in roughly 360 days or near to 360 days. They don't know exactly what we know today. They measured it roughly close to 350 to 360 days, and so on and so forth. So this is how by observing the sky, they don't have any modern telescopes or some other tools to aid with their calculations. But there are some clever people like Thales. This is a picture of Thales, who was a man who is considered as one of the 7 sages of the Greek philosophers. And he is one of the very great person in Greek in those times, and he lived around 6th century BCE, and he was challenged once by Egyptians when they were constructing when he went to Egypt. Thales went to Egypt seeking his fame and getting jealous of him. The Egyptian challenged him to measure the height of the pyramid without any measuring tool or without any tape or something. He could not take any stick or any tape or any measuring object, but still with this ingenious method, that claiming that because he was so genius, other people are claiming in Greece that he was so genius. They want to test his genius level, and therefore they challenged him. Is it possible to find height of a pyramid without any calculating things that you can take here? He said, yes, probably I could do, but I need some time for that. They gave him the time. He was observing a day and a time for which he could do this calculation, and when the time arrived, he did that immediately, and people were astonished. They were quite surprised to see his calculation was almost correct, though not exactly. It was almost true, and so he proved his worth in doing such calculations. But what is the time that he was seeking for? The reason is he used the principles of mathematics to find height of and of course the sun from the cosmos. What he knew that the sun rays were parallel. When you were staying in the surface of the earth, the sun rays travel and fall on the object, and those rays will be parallel at each point. Now, the shadow length of any object from the sun at a particular angle at a given point of time at some particular time will make equal length compared to the equal height. That means what we are trying to say is when the angle of depression from the sun rays to the object like pyramid is say 45 degrees, for example. If it is 45 degrees here, this rays here, if it falls out at 45 degrees, then the length of the shadow casted down on the ground will be exactly equal to the height of the pyramid. So this length will be equal, because you know from basic trigonometry that the tan 45 is opposite, tan theta is opposite the adjacent. So opposite side will be equal to the adjacent side when theta is 45 degrees, because tan 45 degrees is 1, which means opposite side is equal to adjacent side. So if you construct a right triangle with this length here, you see that this length of shadow will be equal to height of the pyramid, because this is opposite side, this is adjacent side. So opposite side will be equal to adjacent side when theta is 45 degrees. So he requested his Egyptian friends to just ask him to wait, so that the sun is making 45 degrees exactly, so that the length of the shadow that is casted down is exactly equal to the pyramid. But some error will be crept in naturally. It will not be exact, because when you measure, the sun keeps on moving, isn't it? It will not stay fixed at 45 degrees. So when you take some time in measuring, it will move just some degrees away. So some error will be kept here in this calculation, but still this method is quite remarkable. So this is why I included this in this title, remarkable calculation. So he used the trigonometric basic fact that tan 45 is 1 to measure the height of the pyramid quite beautifully. Okay, but how does he know that the angle of depression is 45 degrees, and the fact that tan 45 is 1 in 6th century BC is quite staggering. So such a remarkable visionary people were there in those days who could know the truth and applied it quite beautifully to find heights of the objects by the aid of astronomical thing like so he applied mathematics by using astronomy to determine the height of the pyramid. This was one of the greatest accomplishment by Thales. In fact, he also used astronomy idea for predicting a solar eclipse, and he by his idea he stopped a great war that's called the Battle of Eclipse. The battle itself is called Battle of Eclipse because the battle was fought nearly for 10 years. It was so many lives were lost in both the sides, and great damage were incurred, and people went to Thales and requested him to stop the war. He was seeking for an occasion. He sought he went to the kings of the opposite parties and said, God has become so sad because of the battle and losing so many lives, and when he has told me that he will give advice to you on a particular day for which you can stop, don't continue after the God's sign. But what actually Thales was thinking was, he was thinking of the day when solar eclipse would take place at the place where the battle was going on. He predicted exactly that such an incident would occur. In fact, it happened on 28th of May 585 BCE. So on that particular day, it was officially the first recorded eclipse, and that was done by Thales, the great man. And you probably could have studied about Thales in basic proportionality theorem. He was credited with the first theorem in mathematics. Okay, just like Tolkappir in Tamil literature, Thales was the first person in mathematics to give a formal theorem and proof. So he was credited as a mathematician who gave the first proof in mathematics, and he was also equally a good philosopher and astronomer. Now, due to his, he knew how the cycle patterns of the eclipse, and particularly solar eclipse, would look like, and he calculated immediately that the solar eclipse would occur at that particular place. It so happened that when the battle was going on, suddenly the eclipse was occurring, and the dark, the bright sky were becoming dark for a few minutes, like a few minutes, about 6 minutes or 8 minutes. Then he went to that place and said, well, this is the message of the God. By God's angriness, The sky, bright sky, has become darkness. So it is time for you to stop the war and get friendly things and move with stop the battle and seek your friendship. And they stopped ultimately with the advice of thing and believing that God has should remove their curse by making this long battle. And therefore the war was stopped and everything became normal. In fact, they became good friends after this. So by the calculation of mathematics and astronomy, Thales could predict the first recorded eclipse and stop a great war. So that if you go to Google and type the battle of eclipse, you can know all the details that I'm talking about. If time permits, you can do it later. He was also credited with uh, getting this equation of similarity of circles. See, people know about similarity of triangles, but Thales knew similarity of circles. Any two circles are similar. Okay, any two circles, whatever may be the radius, they are similar. Therefore, if you take this as moon and this as sun, if you know the radius of the moon, then you can find the radius of the sun by this. So distance by from the observer on the earth to the distance to the moon divided by this distance from the earth to the distance to the sun. If you divide this distance by this distance, that will be equal to radius of the moon by radius of the sun. If you know these three values, you can find this. Or if you know these three values, you can find the distance. So whatever it is, if you know three of them, you can find the fourth because of this similarity property. So people used very clever ideas from geometry to the astronomical objects, and then they deduced very nice equations and determined whatever they want to find. So the next remarkable calculation that I want to tell you is about Eratosthenes. Eratosthenes was one of very great mathematician in Greece, maybe second only to Euclid or something like that. He was also a very notable scientist and astronomer also. What he did was he was credited to be the first person to measure the circumference of the earth. He was first person to measure almost scientifically the correct value of the circumference of the earth. The calculation was a very good history behind that. It's very interesting actually. What he did was this place called Sine in Africa. Okay, at that place he knew that there will be one particular day on the year where there is what day called zero shadow day. That is, the shadow will not fall for a few minutes at that time, maybe at around 12 noon or something like that, or maybe at around 12, not exactly at 12. So he was seeking that incident, that occurrence where there is no shadow of the sun at this point. So he could place a stick over here so that there is no shadow of the stick that is observed. Whereas if there's another person standing at a place called Alexandria, the stick will cast a shadow, very small shadow here. So at the sign, this is called sign. At the place sign, there is no shadow. Whereas at the place Alexandria, which is located at quite distance here, quite a number of distance here, the same place, in the place Alexandria, you see some kind of shadow casted over here. He calculated that this angle here, the shadow length casting this angle here from the pole is 7.2 degrees approximately. This is 7.2 degrees. We are not sure how he guessed this degree here, 7.2 degrees. This is very close to 7 degrees. Okay, and then what he did was he sent camels from this place to Alexandria to Sine to measure the distance that can be. You can measure it through. It was said that he had sent several camels from this place to this place to measure the distance, and it was found that the camels went at a distance of 5,000 stadia. See, the units of measurement for distance is stadia in ancient Greece. Okay, stadia. That's why we even call stadium. Stadium, the modern word for sports, has come from the ancient measurement called stadia. Okay, it's involved in measurement for many athletic sports. Okay, so what by the way that Thales did, like similarity of circles, he found that the whole sphere, which is round in a sphere like a circle, is similar to this sector. So this sector here with 7.2 degrees in this as a central angle, this sector of the circle is similar to the whole circle. Any sector of the circle is similar to the whole circle. Therefore, the central angle of the sector, namely 7.2 degrees, by the central angle of the circle, which is whole circle has central angle, the whole angle around the point, so which is 360 degrees. So the angle made at the sector divided by angle made at the center of the circle, which is 360 degrees, will be equal to this distance that the camel travel, which is, this is the arc length of this sector, this arc length, which is 5000 stadia, by the total arc length. That is what we need to find. The total arc length, if you assume that is the circumference of the earth, that is yes, that I do not know. So the central angle, the ratio of the central angle will be equal to the ratio of the arc length value. So the arc length, measured arc length here is 5000 stadia. The total arc length is yes, that is the circumference of the earth. So if you cross multiply here, this is 1 by 5, 7.2. This is I think it's 25. So this, if you multiply this by 25 or something, you get this, and multiply here. This is 50. 7.2 times 50. If I hope is this one. So if you multiply this here and cross multiply, simplify, you get so this is 50 times this. Okay, 72 times 5 is 360. So this is 1 by 5. This amounts to 1 by 5. So S is 5 times 5000, which is coming up to roughly this value. 50 times 5000. 50 times 5000 is 2,50,000 stadia. So this, see, one stadia is approximately equal to 0.098 miles. So if you multiply this by 0.098 miles, you get approximately 24,663 miles. Now the modern value for the circumference of the earth is 24,901 miles. You see how it's remarkably accurate. The value measured by this great man, Eratosthenes, was very, very near to the modern computed value. The error probably occurred in measuring that the distance traveled by the camel is 5000 stadia. It was later found to be little more than this length, and therefore you have to increase this value so that it comes very near to this. Okay, because of the error that was made here, this difference had occurred. But considering the fact that he used the principle of geometry and the sun's shadow, knowing that zero shadow day occurs, and so using the principles of mathematics and astronomy, he could compute the circumference of Earth quite remarkably. So given the period that he has done around the 2nd century BC, given that point of time, it was quite remarkable. Not today, of course, but given in his time, it was so remarkable to do this calculation. Now, so the next thing that I want to show you is mathematically you can see the sunrise of a given along a given year of a time. So in probably this is 12 in the starting time. This is 3 a.m. This is 6 a.m. This is 9 a.m. So sunrise happens between 6 a.m. and 9 a.m. roughly around 6:45, 7, 6:30 something. So in January, the sunrise happens between around say 7 to 8 p.m. 7 to 8 a.m. here, near to 6:30 to 6:45. So it starts here, and then what happened was, as you increase the month, in February it decreases. That means the sunrise will happen yearly when you increase, when you go near to June. You see, in February and March, you see the sunrise become much earlier. Okay, in May the sunrise is much earlier. You can see here. If you come to May, the sunrise is around very close to 4 p.m., 4 a.m. or something like that. So the sun rises very quickly during the month of May. June, if you come, it is still earlier. So if you take this point here, this is around 3 a.m. You see, the sunrise is much earlier in the month of June. So, and then if you keep on moving away to August, September, October, and along the months of the year, then the sunrise as before, it then goes late and late and late. Then it comes to the same position here. So this graph was observed by astronomers of previous era, and you see how nice it was. It was symmetric, very nice symmetric curve. In fact, this resembles the arc of a sine curve. Not exactly sine curve, but portion of sine curve. And you can obtain this curve through Fourier series expansion of sine function. So by considering Fourier series expansion of sine function, you can get this path traced by the sun throughout the months of a particular year. Okay. Similarly, this is sunset. You know, sunset happens in the evening. So by the month of January, near to 15 is 3 p.m. Okay, this 18 is 6 p.m. So it occurs between 3 p.m. to 6 p.m. Like around in the month of January, it is around 3:30 p.m. In the month of February, it is little more, around 4 p.m. or something like that. So in the sunset will occur in the month of June by say around not in India, of course. This chart is not prepared in India. This is in European country. So you see the sunset around June is after 6 p.m. In fact, even in India, in the month of May or June, you find that there is sun staying in the horizon even at 6:30 p.m. or so. So it will settle down only around 7 o'clock. So around 7 o'clock, it will go down in the month of June, July. And you see this difference here gives the length of the day, because this is sunrise and this is sunset. So this gap here gives the length of daytime in a particular day of a given month in a year. Okay, and you see this maximum gap here occurs during month of June or July. So that's a midsummer for us. So between May and July, if you see these 3 months, so this gap will be more. And if you go beyond that or before that, to the left or right, this gaps close down. And during the month of November and December, the gaps close out south, so you get winter over here, because so this is the night time and this is the daytime. So nighttime is smaller and daytime is larger. Whereas here the daytime is larger, the nighttime is very small during June and July. So this is the graph made in northern hemisphere. If you are staying in southern hemisphere, in a country in the southern hemisphere, the chart will look tilted way. That is, sunrise will be the above way and sunset will be the below way, because you are in the other part of the globe. So depending upon where you lie, but the graph will be symmetrical like this. The shape of the graph doesn't alter, but only the the position will alter. So that's what you get. And using mathematics, in people had found out that March 21st was a day called for which day equals night. So if you want to find equal gap, so March 21st, something like this here, for which this gap will be equal to sum of these two. So if you measure this length on March 21st, that will be equal to sum of this and sum of this. So if you count this value and add these two values, this length will be equal to sum of this length. So this happened day, which means day equals night, when that is the season where the spring begins, that is the warm summer will begin there. And the longest day will occur on June 22nd, that is called summer solstice. And September 23 is again a day where day part is equal to night part. And after September 23, this is the shortest day, December 22nd or something, you get a dark portion more, night portion much longer than the day portion. That is why you see sunset occurs very soonly, around 5 p.m. or 5:30 p.m. during month of December. Okay, so this chart conveys so much meaning to us, and it shows how mathematically the sunset and sunrise occurs. It's quite wonderful, isn't it? Just like a curve shape here. Okay. There are many surprises that you see when you go to astronomy and view mathematically. Especially I'm talking about the Earth. Okay, so when you take the equator, which lies in the central part of the things, so this are called parallel. This is the equator, the middle portion, the equator, and this are called parallels. The lines parallel to equators are called parallels. Okay, and these lines are called meridians. Those are called meridians. The prime meridian is a line which joins exactly the south pole to the north pole. The other meridians also will join them, but this is called the prime meridian because it's the prime meridian is a meridian which joins between 0 degrees and 180 degrees. The other meridians will join in different angles, but prime meridian is from 0 degree to 180 degrees, exactly from starting position to the other extreme position. So this is the prime meridian. Okay, and you see all these angles here where the parallels and meridians meet were right angles. Okay, in fact, in complex analysis, you see this parallels will be treated as the real parts of analytic function, and this meridians can be compared with imaginary part of analytic function. And if you know that if f of z is equal to u plus iv is analytic, then the family of curves u is equal to c1 will cut orthogonally the family of curves v is equal to c2. So if you consider u is equal to c1 and put c1 as 0, c1 is 1, c1 is 2, and if you consider this each of these parallel lines as family of the curves of the form u is equal to c1, they cut orthogonally the family of the curves b is equal to c2, which are family of meridians. So any member in the family of parallels will be orthogonal to the any member of the family of the meridians, because each intersection here is a right angle here. Okay, so this part of thing that you can observe in the shape of the earth. And if you cut the sphere by a knife like structure, or by a plane rather, the plane intersection of a plane and a sphere makes a circle. In particular, if the intersection happens at the center of the sphere, it is called the great circle. If the intersection happens not at the center of the sphere but at some other point on the sphere, then you get a circle called small circle. So these are all small circle. This is a great circle. In fact, just like the great circle is just like the greatest chord in a circle. The great circle in a sphere is similar to the greatest chord, which is diameter for a circle. Okay, there are among several chords, diameter is the largest chord. So among several circles of intersection that you make in a sphere, the largest possible circle is a great circle. Okay, if for a great circle, the center of sphere and great center of the circle that you cut will be equal. But for a small circle, the center of the circle is here, the center of the sphere is different from that. In fact, you do some problems in 3D geometry to find equation of a great circle formed by a sphere cut with a plane. You will be given equation of a plane, you will be given equation of a sphere. Your task is to determine the center of the great circle that is formed and the radius of the great circle. In fact, by theory, you can find that there are infinitely many great circles that you can do, because there are infinitely many meridians. All meridians are great circles. So you can practically see that there are infinitely many great circles that you can form in a sphere, similar to there are infinitely many diameters in a circle. Okay. Now there's another surprising fact that you can see here is, if you start at any point in a and go say some 50 meters here to the top, 50 meters to the right, 50 meters to below, and then 50 meters to the left. So because I'm going same distance top, right, down and below, in terms of astronomical, I start at this point 50 meters north, 50 meters east, 50 meters south, and 50 meters west. I come back to the same position because I do the same amount of I make the same amount of distance in all possible directions, so I should end up at the same position. But if you do this in a surface of a sphere like earth, like structure, unfortunately you won't end at the same point. So this is one of the curious facts. So if for example, if I start at this point, I go 500 meters here, I go 500 kilometers here, 500 kilometers, and then I come 500 kilometers. So this length will be equal to this length. Okay, so you come to the point D, but this length will not be equal to this length. You can see here, as you come down the parallel, the length of this parallel will be more than length of this parallel, and length of this parallel will be more than length of this parallel, and length of this parallel will be more compared to length of this parallel. So if you take the length of the parallel, then this length will be shorter than this particular length. So if you travel 500 kilometers from D to the point E, unfortunately you will not end at the point A. There will be some gap. There will be some difference here. In fact, it was estimated it was around 28 kilometers or 30 kilometer gap that you find here. So unless in 2D shapes, when you travel around and you end up the same point, that won't happen in a spherical surface. You have to do some extra work to go to the same endpoint. So this kind of surprising thing is observed very often in surfaces like sphere. The next beautiful thing that you can observe in a spherical surface is this. Suppose if I take 2 points on a spherical surface, and if I want to if airplane travels from one point to other point, what kind of path that it will take? Maybe if I want to travel, say, from New York to London in a map like this, there are many paths. See, between any 2 points, there are infinitely many paths that are available. So from A to B, for example, I can go directly through a straight line, okay, or I can travel through this path, or I can travel through this path, or I can travel through this path. There are many paths that I wish to travel from A to B. So, for example, from New York to London, if a plane moves, will it go in this way or through this way? So this is the question here. Most probably we would think that the plane will go along blue line from New York to London, or between any 2 points on the map, from one country to another, from one place to another place. So we prefer that way because we have learned in our school that between any 2 points in a plane, the straight line segment is the shortest possible distance, that provides the shortest possible distance between the 2 points considered. Therefore, we strongly believe that the air path travel from New York to London will have shortest path when you travel along blue line compared to the red line. But what actually plane does is it will not travel directly along straight line from this position to this position, but will travel along some curved line. What is that curved line? Only by going that way it can travel in shortest possible time. In fact, for a surface like a sphere, which resembles for an Earth which resembles a sphere, the shortest possible path that can exist between 2 points is called is arc of a great circle. Great circle I showed you here in the slide. So you take, a great circle joining those 2 points on the surface of the Earth, and that will be the case. So if I want to travel from this point to this point from this portion of the Earth to this portion of the Earth, then I will join them by an arc and then form a great circle. So this is a great circle joining these 2 points. So the pilot or flight mechanism will be in such a way that they will draw a great circle between those two positions along the surface of the Earth, and they will travel only along those paths. They do not, for example, travel this way or this way, deviate from this path. Only if you travel through this way, you can get the shortest path and reach the destination within shortest span of time. So this is what people do. So this is one part of application of mathematics to astronomy, particularly in airplanes and other transportation cases. So the great circle play a very important role in transportation problems. Okay. And the other surprising consequences, like if you take any triangle on a surface of Earth like this is an Earth surface of a sphere like this. So this is 90 degrees. This is, I told you, this is the equator. This is the meridian portion. Just now I told you meridian will cut the equator at right angle. So this is 90. This is 90. This in fact is 90. So this sum of the three angles drawn in a surface of a sphere, this is called a spherical triangle, will add up to 270 degrees. That is quite surprising because we learned in our school that sum of three angles in a triangle is only 180 degrees. Sum of all the three angles in any triangle should measure only 180 degrees, two right angles. But here I have a triangle measuring more than 180 degrees. This happens in a geometry called elliptic geometry. And I told you that that's why this shape of the Earth is a special case. It follows a surface called ellipsoid. Okay. So this happens in a surface following elliptic geometry. So for all surfaces pertaining to elliptic geometry, if you draw the triangle on such surfaces, they always have angle sum greater than 180 degrees or pi radians. It always happens so. Whereas if you take on hyperbolic surface, this is elliptic geometry. If you go to hyperbolic geometry and draw a triangle, then the curved triangle will be like this. This is hyperbolic triangle. Okay. In such cases, angle sum will be less than 180 degrees. So when the objects bend like what Earth does, so people may ask me, then teachers who listen to this in the schools, when I said this, then what we have learned or what we have thought is wrong. It's not wrong, but when you confine your surface to be flat surface like a 2D sheet of paper, then the sum of angles is 180 degrees. So for any surface without any curvature, like flat surface, the sum of angles will indeed be 180 degrees in a triangle. But when you go to a surface like bending shapes, like pipe structure, like cylinder or cone or sphere, or like the sheet, folded sheet, resembling the potato chips or something like that. So if you go to such folding types curvatures, then when the angle sum will be greater than 180 degrees for the objects when you are in a surface of positive curvature, whereas the angle sum will be less than 180 degrees when you are in a surface with negative curvature. This surface is hyperbolic geometry surfaces or negative curvature, and this is elliptic geometry or positive curvatures. For positive curvatures, the angle sum will be greater than 180 degrees. For hyperbolic geometry, the angle sum will be less than 180 degrees. For flat surfaces, the angle sum will be exactly equal to 180 degrees. So what we learned in school only this case, but we haven't seen these cases. Okay. See, in fact, I can tell you, to decide what shape the earth is, even today there are some part of people in our globe, they argue and they always strongly believe that the earth is flat. There were big fight battle that was happening in the ancient time. Some people argued that the earth is flat like this. Some people argued that the earth is round, it's a spherical shape. And most of the people who knew mathematics knew for certain that earth is spherical. Like Aristotle knew, Plato, Aristotle are good mathematicians, and of course, people like Pythagoras knew, people like Thales, of course, probably very well knew, and Eratosthenes. See, if Earth was not round, then they could not get this difference in the angles measured, the stick, isn't it? For a flat surface, if the shadow doesn't cast at one place, it should not also cast at the other place also, wherever you are. Only because of the Earth is round in shape, one place there is no shadow, the other place the shadow is casted with some angle. This fact even is a little proof for the fact that Earth is round. But that doesn't convey the fact that Earth is spherical, of course, but it conveys that Earth is not flat, of course. So people like those people who used mathematics effectively to deduce something probably knew that Earth is round, but people doesn't knew much mathematics still argued that Earth is flat. And there are even people today, in today's case, they are called flat earthers. They believe that Earth is flat and they argue with so many things. But I used to tell my students that people had confirmed that Earth is round, though by many problems and many formulas. Even I can show the other slides to you that confirming the fact that Earth is round. But they knew for certain that Earth is round only if they went to the space. So to know how the Earth look like, you have to go out of the Earth and see. So to know yourself, you have to go away from you and see the next dimension. You have to think. Only then you can know about yourself. So this kind of scientific lesson is taught by scientists to us through astronomy. Okay? So know that Earth is round. Only if you leave the Earth, you can know that Earth is round. So only if a person goes to space, leaving the Earth, the atmosphere, they can view the full part of the Earth, and for certain they knew that Earth is round. Unless you are staying in Earth, you can't do that. The ancient people doesn't had the provision of going to space through airplanes or aircrafts or rockets or jets or whatever machines that we have today, and therefore it is problematic for them to decide. Okay, but we are very fortunate to live in a era where we have all such provisions where everything can be measured and get cleared off. The other proof that Earth is round is given through mathematics is this. So this is the Gate Bridge in USA. Okay, Golden Gate Bridge, very famous tourist spot in one of the America. So I had not been to US, so I'm not sure about all these things. I learned only from books and other materials. Okay, so this is called Golden Gate Bridge, which is considered to be one of the very largest sea bridge in the world, one of the very fine structures. So what people had measured is, see, if the Earth is flat, then this pillar joining the bridge should have same length. But they measured that this topmost part of the pillars have some length more than the bottommost part of the length. And they did this calculation. If the Earth is flat, then I will rush through. What they have done is, this portion by circumference of the Earth is equal to this portion by circumference of the Earth. So what you can do is L by 2 pi r is equal to this length, L plus x by 2 pi. This is circumference of the Earth is 2 pi r. Here, if you have to add this height of this pole supporting the bridge, so this is t is height of the pole. So for this larger circle, okay, this portion is L plus x, but the radius becomes r plus t. Okay, So 2 pi times r plus t. If you simplify, you get x is TL by r. You know the values here because of the construction of the Golden Bridge, and you know that the radius of the Earth is 6,371 kilometers roughly. So if you convert this to meters here, because the numerators are in meters, you convert that to meters, you get this meters, which is roughly 4.6 centimeter. So there's difference between the bottom part and the top part is almost 5 centimeters, merely very close to 5 centimeters. And 5 centimeters is very small, as you can see in a scale. So for a very big structure like a Golden Gate structure, this distance, the difference between this length and this length, if you join from topmost part to the topmost part to this point, this distance in the topmost point will be larger by 5 centimeters compared to this distance. But that is very negligible because this is a very lengthy part and you can't see it. But the length is positive because of the curvature of the Earth. Because the Earth has some positive curvature, this length is a positive value. You don't get 0 here because the answer is a non-zero number. You get this non-zero. So again, confirming the fact that Earth is wrong. Okay. And this is how eclipses were observed. So I don't, because the idea about eclipse is well known to others. So you know that when moon comes between Earth and Sun, you get solar eclipse, and the other way you get lunar eclipse. When okay, so to along the when the eclipse occurs, this diameter. If I want to know, for example, the diameter of the Sun, that can be measured when eclipse occurs. See, to measure the diameters of the celestial objects, the calculation will be pretty accurate during the part of the eclipse, because during the non-eclipse time, the portions will be the objects that you consider will not be in collinear position. The best thing that you get in when the eclipse takes place is when the objects will be in the same line, when they are collinear. The eclipse, of course, the converse is not true. The eclipse occurs when the objects are in collinear, but when the objects are in collinear, the eclipse need not occur. So the other way it is not true. Only at certain nodal points and at certain specific positions in a given point of time, the eclipse occurs. But whenever eclipse occurs, the three celestial objects, namely the Sun, Moon, and Earth, will be in the same straight line. Depending upon which is intercepted between, you get solar eclipse or lunar eclipse. Okay. And moreover, the portion in umbra region here is where you can observe the solar eclipse. So if you are staying at this part of the Earth, you don't experience this eclipse here. So only if you stay in this portion where the umbra portion region is recorded here, only for those people the whole part of solar eclipse can be observed. Whereas if you stay here, little bit of partial eclipse can be seen. But when you stay at this portion of the Earth, no portion of the solar eclipse can be observed. So depending upon where you are placed during the occurrence of the eclipse, you can either view it completely or you can view it partially, or you may not be in a position to view it at all. The other parts of the globe you can view it. Okay. So because of the collinearity of the objects, you can measure the unknown thing quite beautifully. So it is difficult to know the diameter of the Sun because Sun is too hot to even look at, isn't it? So to measure the diameter of the Sun, but diameter of the Earth and the Moon were quite easily measured. So if I know the diameter of the Earth and diameter of the Moon, and distance from the Sun to the Earth and distance from the Sun to the Earth to the Moon, then you get this proportion. Because you see this triangle here from Earth to Moon, this triangle is similar to the triangle formed by Earth to the Sun. So this larger triangle is similar to the smaller triangle. And therefore, this radius, this distance from Earth to Moon divided by, so I have taken the other way, diameter of the Sun by diameter of the Moon, which is this length, this is in meters, is equal to this distance. Because the two triangles are similar, the corresponding ratio of the corresponding sides are proportional. So we have taken the numerator, diameter of the Sun. So this numerator is distance from Earth to Sun. So this diameter by this diameter is equal to this distance by this distance. If you compute this, then it's easy to find. So this is how people used to calculate, and you learn a big lesson here. From this answer, what you can do is, if you divide the distance of the Earth to the Sun by this answer, by the diameter of the Sun, you get this value. As well as if you divide this distance, 2,40,000 miles, by this diameter, 2170 diameter of the Moon, you get same answer. Because these answers are same, at the point of time of eclipse, one encloses the other. That is, one covers the other portion. They look like same size. When you look at even Jupiter, it looks like a small ball, because it is not only it is a distance, because of this fact that this position of one covering the other, though of different size. Moon is very, very small in size compared to the Earth, as well as the Sun. See, Moon is small comparison with Earth as well as to the Sun. Very small, in fact, comparison to the Sun. But still, how can Moon can cover a big object Earth? That is because of this fact that this ratio is constant. Because this ratio is constant, some portion of the Moon, this portion at least, covering to umbra portion region, will cover the portion of the Sun. So for this people, Earth will not be visible. The Sun rays will not be visible when you stay here. Moon can cover because the ratio is constant. So this kind of small observations in astronomical happenings can be observed by mathematics. And if you take spirals, you can see spirals in several galaxies and several objects and flowers and other things. The DNA has two spirals, okay, one going this way, the other one going double helix, okay? And so spiral looks like this. And so this spiral shape is the mathematical equation here, that's called equiangular spiral, or so this is comprised of two equiangular spiral, one going clockwise, the other one going anti-clockwise, or galaxy. Okay, so equiangular spiral is a special mathematical curve described by this way. It has a beautiful property that the distance here goes in a geometric progression. The geometric progression is this theta value. So, and moreover, if you, this is the radius vector, this is the tangent drawn at any point, you see the angle between the radius vector and the tangent is always constant at any position on the equiangular spiral, which means that the best part in having spiral shape is to accommodate as much as packing as possible of the objects in a very minimum portion. That is, in a small region, if you want to pack as many things as possible, the best possible shape that nature chooses was spiral shape. Because of this spiral shape that the nature chooses, it can accommodate so many things with it, so many atoms within it, compared to different shapes. So if the nature has chosen some other shape, then the number of things that it can accommodate is much lesser than choosing this spiral shape. Because of this fact, this mathematical fact, that the angles are same. Okay, so I wonder how nature knew this mathematical fact in choosing this spiral shape, including the galaxies that you see in these different parts of the universe. Okay, and there's another beautiful spiral called equiangular spiral, but this kind of spiral is not visible in the cosmos. This is only for mathematical part. Okay. The other things that you can do I will rush through because we are running out of time. This number 2.5 is very special for idea called what is called a stellar magnitude, which refers to the brightness of the different stars. So what you can do is the second magnitude stars are n times brighter or n times less brighter than the first magnitude stars. The third magnitude stars are n times lesser magnitude than the second magnitude stars, and so on and so forth. So because of this, third magnitude stars compared with first magnitude stars will be n square times lesser brighter, because third with second is n times, second with first is n. So this n will be multiplied with this n when you go from 3 to 1. 3 to 1 is n times n, that is n square times. Similarly, the fourth magnitude stars compared with first magnitude stars will be n cube times lesser brighter. And you know that among this brighter, if you start with the most brightest star with magnitude 1, then magnitude 2 is 2.5 times that. This is 2.5 times this. If you go, you get 100 when you reach the magnitude of 6. So we can stop up to n power 5 here at the 6th position. Magnitude 6, we can stop. So because this value is 100 here, you can equate the n power 5 to 100. So n is square root of fifth root of 100, which is approximately 2.51188. and that we can round it off to 2.5. So this 2.5 is a magic number with respect to brightness of stars. So because this determines how bright a star is compared to other star. For example, the sun is brighter by this much amount, 447,454 times in comparison with the moon, because the stellar magnitude of sun is this, stellar magnitude of the moon is this, and if you divide one upon the other, you get this difference. So this ratio gives the amount of brightness than one star in comparison to the other star. Okay, so this, any for all such calculations, the basic factor, the base number is 2.5. So 2.5 is a number measuring stellar magnitude. Okay, and there's another interesting discovery that was made. This was a huge part of the story. So I will just give the basic fact here. So you start with numbers which are powers of 2 except 2, 0. The 2, of course, 0 can be treated as power of 2 when you write 2 power minus infinity. So this is 2 power minus infinity. This is 2 power 0. This is 2 power 1. This is 2 square, 2 cube, 2 power 4, 2 power 5, 2 power 6, 2 power 7, 2 power 8. So powers of 2 consecutively except the first term, which is 0. What you do is multiply by 0.3 each of these numbers. So 1 times 0 times 0.3 is 0. 1 times 0.3 is 0.3, 2 times 0.3 is 0.6, 4 times 0.3 is 1.2. So multiply each of this number by 0.3 and then add 0.4 to it. So add 0 to 0.4 to get 0.4. So add 0.4 to each of these numbers. You get this resulting numbers. So what we have done is encapsulated in this formula. Okay, so you take powers of 2, multiply by 0.3 and add 0.4 to that. You get these numbers. Okay. So this law was predicted by two astronomers, Titius and Bode. So this is called Titius-Bode's law. But when they made this calculation, they found that there is something missing out here. This value 2.8 radius from Bode's law and observed radius, actual radius. Okay, these numbers are very close, as you can see. What does this specify? So if you take diameter of, say, Mercury and divide that by diameter of Earth, you get 0.387 something, roughly close to 0.39. If you take diameter of Venus and divide by diameter of Earth, you get 0.72 something. If you take diameter of Earth and divide by diameter of Earth, because you're dividing same numbers, you get 1. If you take diameter of Mars and divide by diameter of Earth, you get roughly 1.6 or 1.5, something like that. This is according to the law predicted here by this formula. This is by actual calculation value, astronomical calculation value. So they saw these numbers agreeing for all the known planets, but this law predicted one other value here, 2.8. Astronomers got confused. What could come here? Because you see, all the known planets are covered here: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. Everything is covered here. But so what could come here? This is where they got confused. Okay, so something is left out, or they need to discover something more, is what was going on to the astronomers' mind. Because this law predicts that there should be something coming over here. In fact, later astronomers and mathematicians found that it was not a planet actually, but a co-planet or a smaller planet called Dwarf Planet, which is planet-like an object, not exactly planet, but it's a very small size, looking like a planet, but revolving on its own object, in one orbit rather, in one axis. So that is called Dwarf Planet. In fact, they found that, so you see the gap between Mars and Jupiter. In fact, not only one such thing they found string of several dwarf planets, like stone-like objects. So they are not planets like this, but they are stone-like objects, but revolving in their orbits. So there are plenty of such, not one. Ceres was just one of such things first discovered, but between Jupiter and Mars, as predicted by this law, very simple mathematical law, they found lots and lots of now what we call asteroids. So these objects are asteroids, and this portion is called asteroid belt. Okay, this portion is called asteroid. So the whole new creation of asteroid belt was discovered by seeking the gap between Mars and Jupiter. So the mathematical law predicted by Titius and Bode help astronomers to discover a whole new universe here of new orbit containing this, probably this what we call asteroid belt. Some asteroids also come very close to the orbit of Jupiter. They are very close to the orbit of Jupiter. So this new discovery was possible in astronomy because of mathematics, because of the Titius-Bode's law. And this is my Easter formula. So those who are interested in computing, I did this few years ago. Even I have published a paper on finding day of a given date, giving the whole idea of how calendars work and what's the reason for the terms in the formula. And I have given a detailed description of the derivation of such formula for finding day of a day, given date. And this is of course about what is called the Easter day calculation. We can rush through for this year. This year is 2021. So if you take year number as y, which is 2021, a is a reminder when the year is divided by 19. So if you divide 2021 by 19, you get a remainder of 7, because 2014 is divisible by 19, as you can check it. Okay, so you get remainder 7. That is my a. Small a is 7 for this particular year. B is a reminder when 11a plus 5 is divided by 30. So 11 times 7 is 77 plus 5, 82. When you divide 82 by 30, the remainder is 22, isn't it? This is 82. 82 divided by 30. This nearest multiple is 60. So if you subtract 60 from 82, you get 22. So B is 22. So C is B plus 1 if either B is 0 or this, or else C is B. C is not coming to this, B is not in this range, therefore B is becoming 22. C is also 22 because B doesn't fall in this range. Okay, so C is 22. So if C lies between 1 to 19, then the Easter month is April. Whereas if C lies in this range, then the Easter month is March. See, Easter month will happen only in March or April. Okay, you get. In fact, there's a predictable date. It is between 21st March to 19th of April or something. I don't remember exactly, but something behind that. Okay, between these two ranges, it is between 20th of March to 19th of April. This is the maximum possible range for Easter to occur. Okay, now listen. C value here is 22. 22 falls in this range. So the Easter month, according to for this year, should be March. But we don't have to not stop it. We want to find the date here. D is the date number. That is reminder when 50 minus C is divided by 31. C is 22. 50 minus 22 is 28. If you divide 28 by 31, the remainder is 28 rather. So I got D as 28. So the calculation says that Easter day date falls on the Sunday following the date D given by steps 4 and 5. So according to this calculation, Easter day falls on March of 28. And if you March of 28 is a Sunday, so the following Sunday. What is the following Sunday after March 28? It is up to April 4th. So the April 4th is the Easter date for this month, this particular year, and therefore it was measured correctly. In fact, this technique works for all years between 1900 to 2199. When I published this in Wikipedia, they had put this in computers page, but 1 year ago or 1.5 years ago, they removed it. I do not know what's the reason for removal, but it was there earlier. And I will be probably publishing this as a big paper in a big journal in future. I didn't find time to do all these calculations, but some part of during my free time work, I did this calculation. This is possibly the most simplest calculation for finding Easter day compared to other formulas that is available. And there's one other, this is my last thing before I wind up. So one beautiful equation called Drake's equation. So these are all the factors that you need to know to compute this value. In fact, using this Drake's formula, people had worked out. This was given by American scientist Drake, and therefore it's called Drake's equation. The problem with this equation is this factors here, this numbers were very uncertain. We can't judge these values, but these values we can judge. So among this product of 7 terms in the right hand side, these 3 terms are certain. This can be certainly given, but these 4 terms are little uncertain, especially the last 2 are very uncertain. Therefore, it's not possible to find the product to the exact number and find how possible that we are searching for whether there's an alien in the outer space or not. In fact, there's a big search called SETI, Search for Extraterrestrial Intelligence. That's called the big team searching for this, and that team is called SETI, SETI. So those who are interested can go to the Google and find the other details by just typing SETI, SETI. And so, though the formula is not practically useful for us, it does conveys a very important point that if you find the probability of occurrence of other living beings in the space, outer space, in fact, the probability is quite huge. In fact, it's more than 50% chance. So this formula says there's more than 50% of chance that there will be some species other than humans who can live at some point in the space. In fact, people were analyzing so far. In fact, some scientists have now said that the other species need not be human. They can be like fungi or bacteria or some kind of insect or some kind of other creatures also. They need not be exactly as aliens as predicted, as showcased in the Hollywood films with green structure and big ears and big nose and something like that. So it may not be like that. That is for cinemas. But those creatures, if at all there is something, would look like not necessarily like humans, but they still can have a large possibility of existing, because they had found many algae and many fungi existing in different planets very, very far away from our Earth. So this formula predicts the possibility of such occurrences, but we are not sure how they look like. So this is a very important and interesting equation which has spurred great amount of research and interest in alien life population. So